Chapter 2, Protecting the Ozone Layer, Part 4. This lecture will cover stratospheric ozone destruction, CFCs, the culprit we've identified behind the destruction, the Antarctic ozone hole, our responses to the discovery of the ozone hole, and CFC replacements. Just a review on what we've studied so far. The ozone layer is in the stratosphere, and it occupies a portion of the stratosphere, roughly 15 to 30 kilometers in altitude above the surface of the Earth. And remember, it's a band where the concentration of ozone is at a maximum. And smog, it's a little bit of ozone at the very surface of the Earth, the very bottom of the troposphere, due to pollutants produced by humans. The ozone layer is our protection from dangerous ultraviolet radiation. Ozone is really not a significant gas in terms of concentration in our atmosphere. Nitrogen and oxygen are much more predominant. If we were to condense all this ozone into one place, it would just make an extremely tiny layer at the Earth's surface. So this ozone is spread out over a band, and that's what's acting as a shield in the stratosphere. It tends to be produced more at the tropics and then flow upwards to the poles. So again, here's the layers of atmosphere. We've got the troposphere down here. The pollution, ozone pollution, is produced at the very bottom. Then we have the ozone layer, the lower part of the stratosphere. And if you recall, ultraviolet light is our high energy light. It's more energetic than visible light. It has a shorter wavelength. Molecules can interact with visible light. They can absorb light and vibrate, or they can, if they absorb enough light, they can break apart. An absorption spectrum is a graph of light absorbed versus wavelength. So it looks something like this. We'll look more at absorption in the greenhouse gases chapter. This is just showing the absorption spectrum of a dye, just a colored dye. So this particular molecule that is acting as a dye tends to absorb light of this frequency. Let's now watch a short film on the history of the ozone hole. So this picture here shows the month changing and the year changing as well. And if you look, you can see that over the course of a year, the ozone hole becomes thinner and thinner over the Antarctica, and it peaks in its thinness right around September and October. And then it thickens a little bit more once we pass September and October. And you can look at the color scale. Blue is less ozone. The concentration of ozone is low, versus the colors on the right-hand side of the scale are greater ozone concentrations. So there is fluctuations over the course of the year, but even taking into account those fluctuations in ozone concentration, significant decreases in ozone are observed. And remember, if you think of the Chapman cycle, ozone will break down and then reform. It is a cyclical process, right? We have high energy light hitting oxygen, it's breaking apart. And then the ozone, if it collides with one of those single oxygen atoms, it will also, and if there's some UV radiation, it will break apart. So this occurs naturally. And there are other causes that can accelerate ozone depletion that we would consider natural. Water vapor, if hit by light, can form these hydrogen and hydroxyl free radical catalysts. Now let's try to explain what that long statement means. A radical is essentially an atom that does not meet our octet rule in Lewis structures. These creatures here, this is not satisfying our octet rule. It has an unpaired electron. We never looked at molecules with a single unpaired electron. That's because these are highly, highly reactive. Now, what is a catalyst? We talked about catalysts briefly. They lower the amount of energy necessary for a reaction to occur. So let's say you have a certain amount of energy in a system. With that energy in the system, say only 50% of the ozone molecules break down. Now, with the same amount of energy, and if you add a catalyst, all of a sudden, you have enough energy to break down 100% of those molecules. So a catalyst lowers the necessary energy for a reaction to occur. And so once these radicals, these catalysts, are formed, they accelerate the breakdown of ozone. Another aspect to catalysts is that they are regenerated. They play a role in the reaction, but at the end of the reaction, they're still around, which means they can react again. The other main natural cause of ozone destruction is nitrogen monoxide radicals, and those form when you have lightning strike air. And then these radicals can also cause a breakdown of ozone. So a thinker buddy question. Ozone in the troposphere acts as a pollutant. But does ozone in the troposphere increase the level of ozone in the stratosphere? Why or why not? So ozone will undergo chemical reactions in the troposphere, and it will break down fairly rapidly. It's not stable enough to travel all the way up into the stratosphere. And compared to the amounts of ozone in the ozone layer, even if it could, it wouldn't be a significant contribution. The levels of tropospheric ozone, however, are significant enough to cause respiratory illness and smog and other problems. And just another note, ozone is easier to break apart. If you recall, the bonds are weaker. We're talking about bonds that are closer to single bonds, not as strong as double bonds. So it takes less to break it apart than in oxygen gas. Now let's talk about chlorofluorocarbons, otherwise known as CFCs. These are industrially made chemicals that also act as catalysts to break down ozone, throwing off the kind of natural balance of ozone production and destruction in the atmosphere. So one is Freon 11, and another one is Freon 12. Let's watch a short clip on the history of CFCs. So, as you saw, some advantages are that they're non-toxic, they're not reactive, non-flammable, low boiling points, not water soluble. They can be used as refrigerant gases, in aerosol cans. They can make styrofoam, insulation, can be used as a solvent. And then halons, which are similar to CFCs, they also contain bromine in addition to chlorine and fluorine, can be used as fire retardants. So a lot of uses, many advantages. And this is a picture of a halon. You could see the structure is very similar to the two types of freon we saw in the previous slide. So let's take a look. So here we have sunlight hitting a CFC. A chlorine atom breaks apart and combines with ozone, destroying it. And look, it's regenerated as a catalyst. Again, it strikes ozone and breaks it apart and is regenerated. And it is destroyed again by the same chlorine atom. So one chlorine atom can destroy many, many ozone molecules. And this is the chemical formula down here, the chemical equation. Chlorine hits the ozone for this ClO radical, and then that can break apart, and the net reaction is essentially ozone converting to oxygen. So it's this chlorine radical which causes ozone destruction. So the CFC, again, UV light, that chlorine pops off. That chlorine can then strike an ozone molecule, and the chlorine radical is regenerated. It's a catalyst. It's not used up, so a single chlorine atom can destroy 50 ozone molecules per day, roughly. We have data showing that as concentrations of chlorine radicals increase, ozone concentrations decrease. So here we have on the right-hand side chlorine concentration in parts per billion, and then ozone concentrations in parts per billion. This slide just summarizes our different sources of ozone destruction. There are natural sources. Water can break down into hydroxyl radicals. Lightning can form these nitrogen monoxide radicals. And then there's industrially made. The CFCs and the halons, they form these other radicals that can react with ozone. Now, the hole over Antarctica is larger than the ozone hole in the North Pole. And the reason being is that it's much colder in the South Pole. And that those cold temperatures cause the creation of these unique clouds called polar stratospheric clouds. And they basically act as a scaffolding or a place for these reactions that break ozone down to occur. They look beautiful, but they're deadly to ozone. These clouds form most frequently from September to November. And that's why if you look at this time lapse, we're starting in August, and you can see lower concentrations of ozone are blue and black, and right around September, okay, going through October, that's where our lowest concentration of ozone occurs. So you see these seasonal ozone fluctuations. You see the ozone decreasing around September, October due to these polar stratospheric clouds. But we can look just at the concentration of ozone during October. The time when the ozone concentration is at its lowest. And if you see here, even taking those fluctuations into account, since we're looking just at October, we see a decrease in concentration of ozone, a third as much ozone in year 2000 compared with 1960. Uh-oh. And then you can see here, this shows the actual fluctuations in this data. Okay, fluctuations, fluctuations. Here's the average, this dashed line. And wait a minute, uh-oh. These fluctuations are now hovering over a lower region. Okay, so even taking fluctuations into account, ozone is becoming more and more depleted. Now, the decrease in ozone is not as significant in the northern hemisphere. It's a little smaller. So take a look at that graph and see if you can articulate why you think the Arctic ozone is thinning a little less than Antarctic. So we mentioned that the Earth is tilted. The northern hemisphere is closer to the sun and therefore warmer. And if you look at this graph here, we've got this line that says Psc Formation, those polar stratospheric cloud formations. This is the temperature where if you go below that temperature, you have an increased number of polar stratospheric clouds. So in the Antarctica, it tends to be below that required temperature for the majority of the year, particularly in September and October, compared with the Arctic region. So the Arctic region has less polar stratospheric clouds, in turn less production of the chlorine radical, which breaks down the ozone. Because remember, those polar stratospheric clouds are important to provide a scaffolding for the reaction to occur. Another Thinker Buddy question. You have seen images that show a large area of dark blue or black centered on Antarctica. Which statement best explains the dark blue color in these images? These are A. Real color photographs showing the sky to be dark blue over the poles. B. False color images in which dark blue represents very low levels of stratospheric ozone. C. Real color photographs that represent the UV index in that region. D. False color images in which dark blue represents very high ozone concentrations. So B is correct. These are false color images. Dark blue represents low levels of stratospheric ozone. We're using colors to simplify our view and show the regions which have low ozone. So what have we done in response to the ozone depletion? Well, in 1978, we banned CFC as a propellant for spray cans. In 1985, there was a convention to put together policies to protect the ozone layer. And then in 1987, the Montreal Protocols on substances that deplete the ozone layer was passed and agreed to globally. And then in 1990, CFCs were banned as foaming agents in North America. So here we have a graph of the thousands of tons of CFCs and the year, and you can see the effect of the Montreal Protocol. The amount of CFCs has dropped dramatically. So those chlorine radicals will eventually combine with hydrogen and be removed from the atmosphere. The peak of chlorine radicals occurred in 1999. We're hoping that in 2050 there will no longer be an ozone hole. This picture here just shows very low concentrations are blue, higher concentrations are red. So with the Montreal Protocol, we're hoping that there are no regions of dark blue, more yellow-red. And then without the Montreal Protocol, it was predicted that the ozone hole would get larger and larger, and eventually ozone would thin around the entire globe, which could have had devastating impacts. But what do? CFCs have played a huge role in our ability to refrigerate foods, protect ourselves from food poisoning. So what do? We have to consider developing alternate compounds, and we have to look at toxicity, flammability, and stability. We want something stable, but we don't want it too stable because we don't want it to build up in the atmosphere. And a lot of the alternatives to CFCs are, unfortunately, greenhouse gases. So these chlorodifluoromethane and dichlorofluoroethane are some of the replacements being used. They don't form chlorine radicals as readily, but they do influence global warming, and we'll talk about that in the chapter on global warming. What can you do in your day-to-day life? Make sure your conditioners are serviced, and you check them regularly for leaks. Make sure cars and refrigerators don't use CFC as a refrigerant. You don't want to purchase any vehicles or refrigerators that are still using CFCs. I think that would be fairly difficult in North America. Try to avoid dry cleaning. Some of the dry cleaning chemicals also form chlorine radicals. And then use pump dispensers. Don't use anything that uses propellants. And definitely make sure your old refrigerators and old air conditioners are properly disposed of. This ends the last part of Chapter 2.